Welcome back. We are discussing ohm meters and particularly the scale of the ohm meter. And in our last video, you have seen that so the scale of the ohm meter is non-uniform. 0 on one side, infinite on the other side, and the center of the scale correspond to the unknown resistance equal to the total internal resistance of the circuit. Now, and we also said that if the R internal is equal to 1 kilo ohm, then with this ohm meter we can measure resistance values which is say between 1/3 of a kilo ohm and 3 kilo ohm quite accurately, but it's difficult to measure resistance value which is higher than 3 kilo ohm or much higher than 3 kilo ohm, or which is close to 0 or lower than this 1/3 of a kilo ohm. Now, suppose I have a resistance which I know has a value of say 10 kilo ohm or around 10 kilo ohm, then this ohm meter is not good to measure that resistance. Or if I have a resistance whose value I know is about 100 ohm or 50 ohm, again then this particular ohm meter is not good to measure that resistance. What can we do? We need another ohm meter, another ohm meter whose scale will have the center point. So this center point equal to the tentative value of the unknown resistance that we are measuring. Okay, so if the tentative value of Rx is equal to say 10 kilo ohm, then the center should have 10 kilo ohm marking. How is that possible? Because the center always correspond to the value of the total internal resistance. What is the total internal resistance? Let's draw this circuit once again. The battery, then we have the Rx, the unknown resistance, then we may have everything else, battery resistance, Ri, then we may have the meter resistance, everything. So that's everything together is the total internal resistance. So everything means everything here. Okay, so everything here is the total internal resistance, and the center point always correspond to half of the equal to the total internal resistance, provided the extreme right position correspond to Rx equal to 0. That is what we have seen. Okay. Now we need the center point to have a value of 10 kilo ohm. This is only possible. This is possible only if we can change R internal equal to 10 kilo ohm. Okay, but that's not difficult. According to our previous example, where we had R internal equal to say 1 kilo ohm, now we can add a series resistance. So let's add a series resistance here, which may be 9 kilo ohm. Call it R1. So choose the value of R1 so that the total internal resistance becomes 10 kilo ohm. Okay, then the scale of the meter will be altered. So choose R1 appropriately so that R internal, which is same as Ri plus R meter plus R1, this should be equal to 10 kilo or whatever value you desire, or whatever is the value of tentative value of Rx that you want to measure. Okay, and therefore the scale of this meter will get altered like this. This side will be 0 ohm, this position will become 10 kilo ohm. Once again, this is same as R internal, but now we have changed the value of R internal by adding an appropriate series resistance in the circuit, and this position will again correspond to 3 times R internal, which will now be equal to 3 kilo ohm. This position will equal to 1/3 of R internal, which is same as now 10 by 3 kilo ohm. Okay, so now we can measure any resistance between 3 kilo ohm and 30 kilo ohm with good enough accuracy. So now we can measure Rx between 3 kilo ohm and 30 kilo ohm with enough accuracy. Okay, and if I want to measure something like 1 mega ohm, I have to add a higher value of R1 so that this becomes 1 mega ohm, and so on. So this is how we can change the scale of the ohm meter. So this topic that we are discussing today, we can call it, so let's give it a name, scale changing of an ohm meter. So now let us write two desirable conditions for an ohm meter. These desirable conditions for an ohm meter. One of them we already have seen, we already have mentioned, is that Rx equal to 0 should correspond to the extreme right position, and the second thing is that the center position should indicate a value of Rx close to the tentative value of Rx, unknown resistance. So if I am measuring an unknown resistance, I generally will have an idea of the value of Rx. Is it of the order of 10 ohms or 100 ohms or kilo ohms or mega ohms? So I may have a tentative idea, and accordingly I should have the scale of the meter. Somehow I have to adjust the scale of the meter so that the center position is has a value which is close to the tentative value of the Rx, and this condition we can also write as that R internal, okay, because the center position indicates R internal and we want this value to be close to the tentative value of the unknown resistance, which means R internal should be approximately close to the tentative value of Rx. Okay. So, depending on what value of Rx or what range of Rx I want to measure, I should be able to change the R internal, and I also need a provision for adjusting the so that the extreme right position here correspond to Rx equal to 0. Okay. So far we have assumed that the first fact is true, I mean, and we haven't said how to achieve this. And the other requirement, the second requirement, this we already have indicated that by choosing the value of the series resistance R1, we can make this second criteria fulfilled. Okay. So now let's talk about how we can adjust the circuit so that Rx equal to 0 correspond to extreme right position. So how to achieve first criteria, that means extreme right correspond to Rx equal to 0. So how to achieve that? And okay, so how we will do it? So this will be done by, so let me draw the circuit. So I am drawing these terminals because Rx is an external element that will connect to the circuit, and everything else is internal to the circuit, internal to the ohm meter. Okay. Now so here we will have the R1 in series, and then we will have the meter. So this can be a PMMC meter, for example. This R1 we will need, this is primarily to adjust Rx, not Rx, R internal is equal to tentative value of Rx. Okay. And we will put a shunt, call it R2, okay, R1 and R2. So we will put a shunt with this ammeter. So this is an ammeter. This can be a PMMC meter, for example. Okay, and we will put as a shunt just like ordinary ammeters. And what is the purpose of this shunt? This shunt will bypass some amount of current which flows in the main circuit. If this current is I, only a fraction of this current will flow through this meter, and the remaining part will go through Ri, and thereby this will alter the effective full scale deflection current of this combination R2 and the meter in parallel. So the effective full scale deflection current of this arrangement will get increased. For example, say if I call for this meter say for this meter the internal resistance is Rm. So the meter has a coil resistance, you can say coil resistance of Rm, and the full scale deflection current of this meter is IFSD. So let us call it IFSD M, M for meter. Okay. Then the effective IF full scale deflection current will be how much? Okay. Say, so if I call it FSD effective, okay, that means the current which flows in this main circuit, I effective full scale deflection current. Okay, if this is the effective full scale deflection current, then the current that goes through the meter is sufficient to bring the pointer to the extreme right. Okay. So then when by this I mean when this amount of current is flowing through the main circuit, the pointer goes to the extreme right, which means at that moment this current will be same as IFSD. Okay, IFSD of M. Okay, so we can write I effective FSD, this is the total current, and then the current divider rule. So the current which will flow through the meter, we can write this as R2 divided by R2 plus Rm. This will be the current through the meter, and then this should be IFSD M, or then we can write IFSD effective will become IFSD of the meter multiplied by R2 plus Rm divided by R2. Okay. Now, by adjusting R2, we can change effective full scale deflection current. Okay. Now, and therefore and thereby we can and thereby we can ensure that Rx equal to 0 correspond to the effective full scale deflection current. So by choosing a proper value of R2 along with a proper value of R1, we can change the effective full scale deflection current, so that when Rx equal to 0, the current that flows will bring the pointer to the full scale position. Okay. So I think this will be more clear if we take some example. Okay. So let's take an example, numeric example. Okay. So say the problem is we have a PMMC meter with full scale deflection current is equal to say 1 milliampere. Okay. And the coil resistance say Rm. So this is the meter resistance. Let's call this 100 ohm. Okay. And we also have, and we have a battery with say EMF is equal to 10 volt and say Ri internal resistance equal to 1 ohm, and the goal is to make an ohm meter with center corresponding to Rx equal to 1 kilo ohm. So, that means this means we want to make a ohm meter which will measure resistances near 1 kilo ohm. Okay. So, how to achieve this? Okay. So, solution. So, first requirement is that our internal, okay, so total internal resistance must be equal to 1 kilo ohm, okay, because we want to measure unknown resistance which is close to 1 kilo ohm. So, the total internal resistance should be 1 kilo ohm. Okay. Now, if so, let us draw the circuit. Okay, and okay, this is also an Ri 1 ohm. This is 100 ohm. Okay, and IFSD is 1 milliampere. Okay, now so this is the point. These are the terminals between which I will connect the external resistance, unknown resistance. Now, we want when this is equal to 0, that means a short circuit like this, the pointer should go to the extreme right, full scale deflection, that is what we want. Now, when this is equal to 0, so according to condition 1 or criteria 1, okay, so we can write here, so this is E equal to 10 volt. So, according to the criteria 1, when we have a short circuit here, then the current that flows through the meter should be 1 milliampere. Now, how much current will flow through the meter? Before that, what will be this current I? This current I, the total current through this short circuit I will be equal to E by, I can write it as R internal, total internal resistance including this Ri, the parallel combination of R2 and Rm, then R1, everything together is R internal. This current is the current through the unknown resistance or this short circuit. Okay. Now, according to criteria 1, I should have meter current, let us write it Im, which will be equal to I multiplied by current divider rule R2 divided by Rm plus R2. This should be equal to 1 milliampere full scale deflection current. Okay. Okay. And we know that I is equal to this. Okay. So, let us put the value E by R internal multiplied by R2 by R2 plus Rm. This is equal to 1 milliampere. Okay. Now, what is the value of R internal? Is here. So this is from criteria 2. Okay, so this is from criteria 2 that the center's position should indicate 1 kilo ohm. So R internal should be 1 kilo ohm. So therefore we can write this as, okay, so let's continue from here. So E is equal to 10 volt divided by R internal is equal to 1 kilo ohm, and this will be multiplied by R2 by R2 plus Rm. This is equal to 1 milliampere. Okay. Now this 10 volt by 1 kilo ohm will be equal to 10 milliampere multiplied by this factor R2 by R2 plus Rm. This is equal to 1 milliampere. Now milliampere you can cancel from both sides. So what we will have is this: 10 is equal to R2 plus Rm by R2. 10 is equal to R2 plus Rm by R2. So this will imply 10 R2 is same as R2 plus Rm, so implying R2 will be Rm by 9, and Rm is given as 100 ohm. So this will be 100 by 9 ohm. So whatever the value is, you can find out. So this way we can find the value of required value of the shunt resistance R2. Now once we know the value of R2, let's find the value of R1. Okay. Now, so R1 is equal to what? So this is the question, next question. Okay. So let's go back to this circuit. We know the total internal resistance is 1 kilo ohm, and so let's write R internal is equal to 1 kilo ohm. Now R internal is same as R1 plus this R2 parallel Rm plus Ri. This is equal to 1 kilo ohm. Now let's write it as R1 plus R2 is, so this will be R2 Rm divided by R2 plus Rm plus Ri. This is equal to 1 kilo ohm. So this will imply R1 plus, in place of R2 we know this is equal to Rm by 9. So let's write it as Rm by 9 multiplied by Rm. Here we will have Rm by 9 plus Rm plus Ri. This is equal to 1 kilo ohm. Now let's solve it. So we will have so let's cancel 1 Rm from the numerator and denominator. So we will have Rm by 9 upstairs, and downstairs we will have so we will have 1 plus 9 is 10 by 9. Okay, so you will have 10 by 9 plus Ri. This is equal to 1 kilo ohm. Please check my calculations. If I make any mistake, please feel free to correct it, and also tell us in our forum. This will also be helpful for your friends. Okay, so now R1 we can write this as, this 9 will cancel, so this will be Rm by 10. So Rm by 10 plus Ri, this is equal to 1000 ohm, 1 kilo ohm, and then now it's very simple. Just put the value. I'll do it very quickly. So this will be 1000 minus Rm by 10. This is 100 by 10. So 10 ohm minus Ri is equal to 1 ohm minus 1. So this will be equal to whatever it is. So this will be 990 minus 981 ohm. Okay, so this way you can find the value of required value of R1 and required value of R2. Okay, so this is the answer. R1 is equal to 981 ohm and R2 is equal to is how much? R2 is this 100 by 9 ohm. Okay, and primarily, so let's recall, so let's summarize this video and finish ohm meter by saying that we have two conditions, two desirable conditions for an ohm meter. Number one side of the scale, that is the right side, should indicate zero resistance, and the second condition is that the center part where we have higher accuracy of measurement, because here the scale is spread out enough. Okay, so the center part should have a value equal to the tentative value of the unknown resistance. So these are the two conditions we would like to have in an ohm meter before we design a ohm meter circuit, and to fulfill two conditions we need two controls. Okay, always if I have two criteria to meet, I need two flexibilities, two controls, and these two controls come to me in the form of R1 and R2. I can change the value of R1, I can change the value of R2 to get two conditions satisfied. This R2 as a bypass resistance will control the full scale deflection, effective full scale deflection current of this arrangement, thereby ensuring that the extreme right position of the meter correspond to Rx equal to 0. And by changing the value of R1, I can change the total internal resistance of the circuit, thereby ensuring the center part of the scale correspond to the tentative unknown resistance. Okay, so thank you. That's all about ohm meters.